Hello, everyone. So yeah, today I'll be talking a bit about resonances. Well, specifically about the rho K-star, the simplest one, one could argue, and the work we've been doing in Edinburgh, essentially mainly in Edinburgh, on a physical paramass simulation of the. So this is part of EuroPLEx, actually. I'm a EuroPLEx fellow. And let's start with some background. So first, some phenomenology facts. So we see a lot of particles in standard model are actually resonances, right? And I'm going to be interested in the QCD resonances here. So the ones that decay through strong force. And they are very fast decaying particles, and then the way that in experiments this has been characterized along like history of particle physics is usually as enhancements in the cross section of certain scattering channel. So here you have E plus E minus, for example, very famous with the rho, and then characterizing the bumps is what. Intuitively, you would do that in experiment. But it turns out that there's a lot of importance in frontier, of precision frontier, and in the standard model due to multi-body final states, which are decay products of resonances. So I have rare multi-body decays here. And the K star, mainly the K pi decay, and the pi pi for the rho, which are the ones we are going to consider in this work. Departing a bit from that, the bumpiness on the cross section can be traced down to an analytical structure of the scattering amplitude, the S matrix, more fundamentally, I would say. And it's before QCD, so you don't need to talk about QCD necessarily to talk about what unstable particles look like. From this description, so by unitarity, you have the mass pole of the particle just shifts into the imaginary, the complex plane. And causality also imposes that the multi-valued, the poles that correspond to the resonances, particles, they are going to be not on the physical sheet where for example, bound states are located, but on the physical sheet, which is analytically connected to the real axis through the branch cut. So these, for example. So at low energies, where QCD is, where we're interested in QCD, the resonances are inherently decaying and binding, which is very, well, turns out to be very difficult to describe. But connecting to QFT, more specifically, we know from LSZ, you connect the scattering amplitude to correlation functions from QFT. And we know that Lattice provides correlation functions non-perturbatively, but there are some things that need to be dealt with. So I would say in this order, because it's nicer to tell the story, Euclidean space metric first. So it's very hard it's a very hard problem to analytically continue noisy data, as we've been seeing these days. And there's also the other approaches like taking large time limits of correlation functions that also imposes a limit on what you can extract from scattering, giving lattice correlators. The other thing that it's very important in lattice observables is that we usually, we are usually interested in periodic, sometimes interested in periodic. Here we're going to concentrate on that, and finite volume space. This imposes some reduced symmetries on the theory, and discrete spectrum also. But the most important is that the box size the dependence on the box size L is what is going to indirectly tell us something about resonances and scattering in general. So the Lusher method that you've heard from yesterday probably already, and the extensions from it, they exploit the dependence on the spectrum, of the spectrum on the box size. So it's not an direct extraction of the scattering from the data, but it's an indirect extraction. So it's basically, I would say conceptually, there are 2 points. The first, that for studying like few body scattering, you neglect exponential surpass effects. It has to do with squeezing of the pion cloud and wrapping of the pion on the periodic lattice. And you concentrate on in the power law corrections coming from the finite volume loops on finite volume correlators, which is what you compute on the lattice. So it turns out that the poles on this skeleton expansion of the scattering amplitude gives you, turns out to be what you're interested about, the finite volume corrections. And then everything's encapsulated after some time, encapsulated in the quantization condition, written angular momentum basis. And so you have the scattering amplitude and some geometrical function f, which depends on the box size. And this is equal 0. This is satisfied at the finite volume energies, which are the poles on the correlator, on the finite volume correlator, on the formalism. So this, of course, you need to use it in simulations. You need to truncate it somehow. So usually we're interested in the lower partial waves in this low energy scattering, and also you need to reduce the angular momentum representations into the lattice E-reps. And after all that, we can constrain the scattering amplitude using lattice QCD data, which is something that's it's pretty much established still a lot of things to explore, but we see that it works, especially for two-body scattering, two-hadron scattering. And so here I enter more into what this project was about, which was the computation of K star and rho. I'm going to concentrate on K star resonances in the resonance parameters of the K star, because it's mostly what I have more finished results on, and towards high precision on these things, which is important for those decays in the future that I talked about in the bikini. We're going to tackle the physical biomass aspect and also the systematics coming from the analysis that the Lusher formalism conventionally makes potentially. So we use, for the simulation, we use grid and hadrons. This is in the context of RBCU UKQCD collaboration. And more specifically, we use just one ensemble, a domain 1 ensemble, 2+1, with the physical biomass. And MPL, if you are worried about exponentially suppressed effects, almost 4, so it's certainly negligible. Yeah. So here we go about the usual, if you are used to this, way of extracting the finite volume energies from the lattice. What I usually do, so is to build a operator basis. That's one of the options, of course. Here I'm using a bilinear and a 2 bilinear for the k-pi and the pi-pi in their respective isospin channels, and the p-wave, which are the channels where the resonances I'm interested about appear. Projected into these EREPs specifically, because the form of the operators that we have, they come from the continuum theory. So, because we kind of start from there, right? So, but what we want is to reduce this, reduce these operators to representations that are irreducible under lattice symmetries in at different total momenta. And yeah, after you do that, you combine these operators, compute correlation functions. We use distillation. I'm not going to talk a lot about that. You can see Felix is going to do a talk more dedicated to that on Friday, and how we implemented that on hadrons. So basically, using that, you can compute these correlator matrices, and yeah. So what you can do now is to solve a variational problem from this correlator matrices. You have several, right? One for each EREP, essentially, that you have access to. So solving this variational problem through the GVP, which is exposed in this equation, gives you access to the energies exponentiated asymptotically in T, and also in this T naught, which is the reference time of the GVP. It's essentially what you're doing with the GVP is imposing orthogonalization through C of T naught. So the orthogonalization, the relation between the eigenvectors here is mediated to C of T naught. Okay, so the GVP gives you access to the lambdas, which is what we use in the end here in this project to compute the energies. But you can also visualize the effective spectrum, I would say, through the log effective mass, and also you can have a look at the effective overlaps, or I would say relative overlaps between the operators, so you can see which operator overlaps mostly with each level here, if you're interested on these things. And this is an overview of the k-pi spectrum what actually goes into the Lucia formalism in this next slides. I also have the pi-pi one at the back if you want to see it, but it's just a lot of levels. So here I'm showing all the reps that don't mix even and odd partial waves, which is a first approach to k-pi scattering. And yeah. So here I'm going to go to the important bit of the systematic analysis of the systematic effects due to the choice of fit ranges on the correlators. So we've done this. We computed these correlators, built matrices. We did the GVP, and we have all these eigenvalues. We have effective masses, better to visualize them. And we want to go from 1 to 2 through the Lucia quantization condition. This gives you a parametrization of the scattering amplitude, which is, for us, is going to be usually one phase shift. For a single channel scattering, it's going to be one phase shift. And the choice of fit ranges in one here. Remember, there are lots of correlators, so you're choosing different fit ranges in each of them. Introduce possible systematics. Of course, if you try all the different combinations, you get a absurd amount of fits to do on this step here. You get a million, I don't know, 10 to the 15 order, 10 to the 15 of these scattering amplitudes here. Not all of them are going to be significant, of course. And we attempt to do a sampling process on this step to evaluate what is the systematics without having to compute all the possibilities, of course, which is nothing. I hope you can see. So the first step, of course, is that we scan. The way we choose to do this, though, we do a correlator fit scan on each of the levels, right? So we have ways of choosing T start and T stop, which are just the time slices where you're scanning. You just impose a minimum number of time slices on each fit. Here you see the principal correlator, the eigenvalue, if you want, and the corresponding effective mass. And we weigh the fit ranges with the AIC. We use this option of AIC in this specific results. So in each correlator, the sampling that we do is based on the distribution given by the histograms of the fit results. So the energies that we extract from the correlators just with one state fits, which are what we do. Of course, we look at other things, but yeah, this is the main result. You see here the orange, just the fit result histogram, and the blue is the weighted one. And in general, what we're doing is that we're replacing the effective mass plot like this by something that are histograms on the effective like a spectrum of histograms. So we combine all these levels step by step, sample by sample, and form this fit range sample. So this is what the previous picture turns into. So just a lot of histograms on each rep. And of course, we choose some amplitude models, which are probably the most common for resonances. So the vanilla Bright-Wigner, which is probably the one everyone sees, and there is one correct with the centrifugal barrier term, which you can also use. Also use the classical effective range expansion for P wave. And given that, we can invert the quantization condition, because this is how I'm going to solve here the fit of the scatter amplitude. So we can find the energies for a given model and parameters of the model. So, which is called inverse Lucier sometimes. And defining this chi-squared, we can fit the spectrum to the model, essentially, with the covariance determined by a bootstrapping of the data. Here is more directly what is being minimized, so it's the spatial residuals. And on the left is the phase shift visualization. Remembering that you don't, I'm not, in this case, I'm not fitting the phase shift directly. I'm fitting the spectrum that is derived from the phase shift. Yeah, minimizing respect to the phase shift. And this is summary, a visualization of results of the K star for the Bright-Wigner, the vanilla one. Here, the statistical below and the systematic just above. The systematic comes from the 2 sigma confidence interval of the histogram, which are just the central values of all the sampled results. I have the G, the coupling on the Bright-Wigner, and the mass, the Bright-Wigner mass also. And they are weighted using the sum of the AICs, which is one of the choices that we did. Here in this case, I'm doing 50,000 samplings. I'm sampling the fit ranges 50,000 times and doing this, reiterating this. And the statistical, it's essentially repeating across bootstrap samples. And this is what we get for the K star visualization of the phase shift. You also have the rho, which I'm not going to talk about too much. It seems like we have less precise determination, but it's still to be confirmed. Another thing that you can look at are pole positions. And returning to what I talked about in the beginning. So you can just plug the phase shift back into the amplitude and find the complex poles. And the mass and the gamma, the width, the pole width, the width in the pole prescription are related to the pole position by this. And here, if you use different models, this is what you get as a 2D histogram. This is what these images are. I just modified a bit the weight so you can see, because as the weight is exponential, it's very difficult to see anything if I don't make a right choice of visualization. So you can also model average them. And this is what you get if you basically model average the first three. And this is essentially taking into account within these models, these three models, the systematic effects from the model dependence. This is a summary for data, for the results with more numbers. For the K star, which is, as I said, what I have more refined now, and a comparison plot here as we go towards the physical biomass, so results in blue compared to the PDG is there. We still have to put some numbers and some other systematics which are likely to be smaller. still deciding on that. And final number for rho is still being cross-checked. So I'm not going to talk too much about that, but it's there. I have some spectrum plots if you want to see at the end. But I'll just jump to the conclusions and the heritage from this project. So we developed, for doing this computation, developed the distillation code in grid and hadrons, if you're interested in that. It's open source. Felix is going to talk more about that on Friday in detail. And so we have the resonance parameters also for the light vector P wave. So the K star is the first computation of physical biomass. The rho, it's not the first. It doesn't matter too much, but just saying. And also we applied model averaging to the Lucia formalism, both in the fit range choice and also the pole position. I mean, you can do model averaging or whatever you want. Just choices that I did here. Yeah, future directions for these projects are other resonance for the same data, just flashing out that this data was, yeah, this took a lot of time to run. And so whatever you can do within the distillation framework to use this data at physical biomass, remembering like the 2+1, domain wall, lattice is very expensive, etc. we can do. So for example, I can try to study kappa, other resonances with the data. We can also look at, we're probably going to look soon at weak decays or time-like form factors. Yeah, everyone wants a continual limit. I don't know when is that possible. When is that going to be possible? But it's on the horizon, let's say. Yeah, thank you. That's it.